Okay, so a horizontal drain pipe 6 meters above sea level empties stormwater into the sea. If the water comes out horizontally and reaches the sea 2 meters out from the pipe, find the initial velocity of the water, correct to one decimal place. Let g be 10 meters per second and neglect air resistance. So that neglect air resistance part of the question kind of like hints at projectile motion that we're dealing with here. Okay, so if we want to see this happening, right? Let's see this happening, and it comes and say that was my water particle, right? Going across. It falls as per projectile motion, and it follows this sort of path. Yeah. Now what they're asking us to solve is what the initial horizontal velocity is. It's been emptied stormwater into the sea. The water comes out horizontally, as shown in this. It moves horizontally across, but it falls due to gravity. And it travels 2 meters away from the pipe, like from the pipe's base, sort of, out. So you can like draw an imaginary pipe or something here if you want to visualize what's going on. Yeah. And so now we are asked to solve for that initial velocity. All right. How do we figure that out? Well, now we're applying projectile motion, right? Now we can use our formulas that we're working with, right? If I have if I'm going to see this happening going on, right? I have my water, and say this is my pipe, yeah, and it's moving out at our initial horizontal velocity, and that's the velocity that I'm solving for. Let's give it a name. Let's just call it u, yeah, and u is this horizontal velocity that I'm solving for, yeah. So that means from the equations that I showed before about projectile motion, I can write that x is equal to ut plus some constant. I'll write this as c1, for example, right? c1. Yeah. Now this constant 1 represents how far from the origin horizontally. So say this is my origin, the base of the pipe. Okay, remember that this height is 6 meters, right? So say my origin is here, like at the origin here, right? So this C1 represents my horizontal displacement. There is no horizontal displacement, only vertical. So this C1 just goes to 0. Yeah, and so I am just left with x is equal to ut. That is convenient. Now, what else can I work with? I can work with my y as well. Y is equal to minus g on 2 t squared plus now my initial vertical velocity. So I'll call that yeah, I'll just call this c2t plus c3. Like I'm going to represent it this way. C3 represents my initial vertical displacement. So that would be my 6 meters. How far away am I from the origin vertically when I start shooting or start my projectile motion? Yeah? And so this C3 represents this 6, which is minus g on 2 t squared. Now what does C2 represent? C2 represents my initial vertical velocity. Since this is being shot out horizontally, there is no vertical part. If there was a vertical part, then this would be what do you say? This would be projected diagonally. The initial velocity itself would be diagonal. If it's horizontal, that means there is no vertical part to it. So C2 would also become 0. And so if this is 0, then this part of the equation is also 0. So then I get plus 6. That, yeah? That's a g, by the way, yeah. And I have my two equations. These are like the ones that we play with most. Okay, now I am solving for u. How we can solve for u is now we can try figuring out what the actual equation of the parabola is, this path itself. And to do this, to find the actual trajectory, we have to get rid of this t, the t's here. And this is what you call eliminating the parameter, because x is defined by t, and so is y. As t changes, my y changes, and so does my x, according to some rule. Yeah, and this is the rule that I'm working with. So then to get rid of this t, we can start doing some substitution. Which one is easier to make t the subject of? This left bit. I just have x over u is equal to t. And then I can substitute back into here. Y is equal to minus g on 2. Now my t is already equal to this, so I'll just substitute this in. X on u squared plus 6. If you want to expand a little bit, minus g on 2. X squared on u squared times plus 6. Okay, that's cool. What do I do with this? I hear you ask. Totally. Well, I want to solve for u. And, well, how does this getting rid of the t help out with this? What I know is a point that this projectile passes through. Remember, I am given that this initial 6 part, but I'm also told about this 2-bit. Yeah? This initial 6 part I already used up for my y, but I can also work with this if I need to. When x is equal to 0, y is equal to 6, and this still carries on here, but it doesn't help me solve u. Yeah? I need another point, and that other point that I'm working with is this 2. So now when we're looking at this final point here, when it falls, this is when y is equal to 0 and x is equal to 2. So now let's just substitute it in here. When x is equal to 2, y equals 0. Let's just work it here. 0 is equal to minus g on 2. Now 2 squared on u squared plus 6. Now that this 2, and this 2, one of those 2's cancel out. Just get minus 2g on u squared plus 6. Okay, now how does this help? Now this is the only unknown variable that I have, which makes this very, very easy to solve. 2g on u squared is equal to 6. Multiply the u squared on both sides. I have 2g is equal to 6u squared. Divide by 6 as well. So I'll just get g on 3 is equal to u squared. U is equal to plus or minus g on 3, the square root. Yeah. Now we take a plus or minus because it's like how the maths work, right? But one of these options doesn't make any sense. What does u represent? U represents my horizontal velocity. The conventions that we work with is that upwards is positive and to the right is positive. Then if my my horizontal drain pipe is emptying out to sea, right? It can only go rightwards. Logically, according to this diagram, the way that I'm working with, it can only go rightwards. You can't get a piece of water that moves to the right and then magically just falls inside the pipe down to the ground. Logically, this does not make sense. This is what this actually shows is that the two u values that make this parabola work. So in some sense, if I projected this all the way back to the minus 2, that would be that negative value, I think, of u. It would work in a similar fashion to that. Anyway, so in this way, the negative option is nullified because it simply does not make sense in this situation. So you would have to say that the negative one doesn't make sense, and so you would only work with the positive square root. In an exam, the same. In this case, we can just get rid of the negative. And that's what u would be equal to. You would have to type this up in the calculator. Remember, we let g is equal to 10. And so then you just type this up in the calculator and then round to 1 decimal place, and you'll be done with this question. Next question. Jack stands at a window at a building. I have my building. This guy, my boy Jack, and he's standing 6.2 meters above the ground. 6.2. Okay, and he throws his keys straight out of the window horizontally. What a smart idea to do. Okay, and he's throwing it horizontally, and he hopes that his friend Tom, who is standing 10.4 meters out from the base. So say I got my buddy Tom here, and he is 10.4 meters away from the base. Yeah, and this is the building. Yeah, so with the windows and all. Yeah, and so my buddy Jack is throwing it out. Yeah, his keys out, and my buddy Tom, he's catching this, yeah? So it's gonna go wee, and it falls, and it lands to this top. That's what he's guessing, yeah? Ignoring air resistance and using 10 meters per second, find the velocity at which Jack needs to throw his keys. So then now, again, just like the situation before, we have an initial position, and we have a final position. This final position is what we're going to work with the same way how we worked with this 2. And the initial position is going to work the same way as how we worked with the 6. Again, our 2 equations that we worked with, I have x is equal to, now I have, let's call this horizontal velocity as well, u in this case, ut. I mean, I can call this u as any other letter. It's just a placeholder, yeah? ut plus c1. And I'd have y is equal to minus gt squared on 2 plus c2t plus c3. Remember, c1, c2, c3 are also placeholders. Okay. Now, c1 represents my initial horizontal displacement. How far from the origin, usually the origin is the base of the building, how far from the origin horizontally do I start off? I start off, the keys, in this case, start off exactly on top of my origin. That's where I place it. So then there is no horizontal displacement yet when time is equal to 0. So that means c1 becomes 0, because at t is equal to 0, x is equal to 0, and y is equal to 6.2. So I can write this as y is equal to 6.2. I can substitute this in as well, and this works as well. If I have x is equal to 0, 0 is equal to u0 plus c1. And so this becomes 0, so 0 is equal to 0 plus c1. c1 has to be equal to 0. This is like the more algebraic way that you would go through this, and this is what you would probably do in an exam. So again, y is equal to 6.2, so I can write 6.2 is equal to minus g. Now instead of t squared, now t is equal to 0. So I have 0 squared on 2 plus c2 0 plus c3. Yeah? Now this is any number times 0 is still 0. This goes to 0. 0. C2, any number times 0, again, is also 0. And C3 is, well, yeah, C3. So I have 6.2 is equal to C3. And that's what you get, my initial vertical displacement. That's what this represents. Okay, so that means my 2 equations, more specifically, I would have x is equal to ut, and my y is equal to minus g on 2 t squared. Remember that 2 can go like between the g and the t, or both of them, or neither. I mean, yeah, like one of them, or like a 1.5 sort of thing. Again, this is just a division, so you can work with any of them. There, interchangeable. Okay, these are, and then I know C3 is plus 6.2. My initial vertical velocity is equal to 0 as well. Remember that it's being thrown horizontally. Being thrown horizontally makes it have no vertical velocity to it, and that's why C2 is equal to 0. Over here, yep. And so these are my 2 equations. Again, the same way as before. I have x on u is equal to t, and then I substitute in. Y is equal to minus g on 2, x on u squared plus 6.2. Yeah? Okay. Now, I need to use this other piece of information. When x is equal to 10.4, y is equal to 0. This way, my using specific points given is usually an indicator to use the actual trajectory of the graph rather than the equations with t in them. Yeah? Okay, so then now when y is equal to 0, x is equal to, not 6.2, 10.4. Let's substitute in. 0 is equal to minus g on 2. 10.4. I'm really messing up the numbers. Whoops, squared plus 6.2. Okay, let's bring that 6.2 to the other side, or this thing to the other side anyway. So then I just get 6.2 is equal to g on 2, 10.4 squared over u squared. if I want to put that squared inside. Yeah. What else do I have next? What I have next is, now I can divide both sides by that bit over there. Just getting me a calculator because I know that will be handy. Where'd my calculator go? Oh. Okay, interesting. Calculator's missing. Okay, so then I have me, now I can multiply both sides by 2. 12.4 is equal to g times 10.4 squared over u squared. Okay, now g is just 10 in this question, I think. Yeah, using g as 10. So then, dividing by 10, then I get 1.24 is equal to 10.4 squared over u squared. Then, if I multiply both sides by u squared, then I get 1.24 u squared is equal to 10.4 squared. Now, I really need a calculator at this point. You know what I'll do? I will go on calculator here. Easy work. Okay. So, scientific calculator. I got me. So now I have 1.24. Okay, now why not? We divide both sides by 1.24. U squared is equal to 10.4 squared over 1.24. Okay, now I can square root both sides. So u is equal to, now I have the plus or minus. Then I have 10.4 that comes out of the square root, and now I have 1.24. You know how square roots work, I'm pretty sure. Okay, so then I have 10.4 divide. Okay, how about I really need a proper calculator for this. Can't find that anywhere. Okay, 10.4 divided by square root. Where's square root sign? Square root. All the actually, how does this work? Okay, wait. I really don't know how this calculator works. Should get that worked out sometime soon. So I took the square root of this, right? And I have 10.4 divided by that. So I'll just round that up. 1.11355. Okay, that. Close enough. And I have 10.4 divided by that. And I'll get 9.339. I'm rounding that. That's around, roughly, 9.339. Yeah? That's a plus or minus there, right? We still have to take both positive and negative cases. Now, as I said before, we take the positive case. Why? Because we took the convention that right is positive and the up is positive, like my axes, yeah? So that the negative answer simply doesn't make sense. Remember, this is a projectile motion to model something that's going on in our everyday world. How things move if they fall with a horizontal and vertical velocity. Yeah? And so then, if I want to approximate, I have 9.3 meters per second. That's what I get as my initial velocity at which Jack has to throw his keys. Yeah? Okay, now waterfall falls 2 meters a second over a vertical cliff. So I have me vertical 5 meters cliff. And this waterfall flows 2 meters a second. How far out from the cliff does it fall? So now my water is falling to this point. How far out is this? Alright, now let's work with our original equations as before. We have x is equal to, now I have a concrete number, so I have 2t plus c1. And y is equal to minus g on 2t squared plus, let's call this c2, t plus c3. Okay, c3 now is 5. Again, I already showed you why it's 5 before. This is my initial vertical displacement, taking the origin as down here. If I took the origin up here, this c3 becomes 0. But it depends all where I take my origin. The usual convention to answering the questions is that you take the origin as the base of the cliff or the building or so on. Yeah. Otherwise, you take it at that point, and the equation doesn't really care where you take the origin. It works the same way. Okay, so then C3 I'm taking as 5, sorry, and C1 now becomes 0 because now we start our projectile motion directly above. Please don't mind my totally straight line. X is equal to t. Okay, so then I have y is equal to, now C2 also represents my vertical initial velocity. This is being flowing horizontally. It starts off horizontally and it flows down. That's how waterfalls go. As far as it goes in my head. Minus g on 2 t squared. So C2 here becomes 0 because there is no initial vertical velocity. So then I get C3, which is also 5. Yeah, that's cool. Now what? We do the same thing as we did the previous questions. This is probably like from the same exercise in the textbook, so they're just practicing the same skill. X on 2 is equal to t. And then we substitute back in. Y is equal to minus g on 2. Now that's x on 2 squared plus 5. Okay, that's a cool equation. But what am I asking? What do I need to know? When it falls, how far from the cliff does it fall? Okay, so that is when y is equal to 0. What is x? So this is now a simple quadratic question. 0 is equal to minus g on 2, x on 2 squared plus 5. A very interesting quirk that you can work with here is that if g is equal to 10, g on 2 is just 5. So I can write minus 5 x on 2 squared plus 5. Often, like, you know, like a more elegant and more mathematical sense would stay with g and just do it the more algebraic way. But this way works about a little faster. Yeah, and if 0 is equal to this, I can divide both sides by 5. Then I have 0 is equal to minus x on 2 whole squared plus 1. Okay, now we can take this to the other side. X on 2 all squared is equal to 1. Square both sides. X on 2 is equal to plus or minus 1. X is equal to plus or minus 2. Now, if it is moving horizontally at 2 meters a second, say to the right, right? This is 2 meters anyway. Even if I took like a negative scenario, like this way, and my waterfall's going this way, right? And in this case, it would be counted as negative 2. They're asking how far out from the cliff does it fall. So in this case, the magnitude is still 2. And this also works as 2. So, you know, let's just take the positive or the absolute value as the magnitude because they're only asking for a distance. So then my amount that it falls is 2 meters. And that's consistent with all these questions. Okay, the next question. Football kicked 12 meters a second. Cross, I think. I'm going to assume diagonal because I'm not given the information that's horizontal. And usually, like when you kick a football and it clears a goalpost, you're taking an assumption that it's diagonal. How does a football being kicked horizontally magically fly up if it doesn't have a ramp, but like, you know, magically fly up? It has to be kicked diagonally at least. Yeah. So now this football being kicked, right? Now I'm in my soccer ball, right? My 10 out of 10 soccer ball. Okay, and it flies and it crosses my amazing post, right? And this post has a height. This height is 4 meters. 4 meters. And the distance from where I launched this from, this distance is 9 meters. Yeah? And now find the angular projection through which the football is kicked. The angular projection is this angle, theta. Yeah? And they're asking what is this angle through which this football is kicked. Okay, this the actual velocity itself it's being launched is the 12 meters. So this is 12 meters per second. Yeah. And so what piece of information do we have? The piece of information that we have first is this velocity, and we have a point that it follows on, a point on the parabola that this ball is taking in its trajectory, right? And this is the clue that that tells you you want to use your trajectory rather than any other parts of the equations that we're working with, right? So to get our trajectory, we have the x and y equations. So that x is equal to, what do we get? We got, well, first, before we get to the x and the y equations, let's split the diagonal velocity, the 12 meters a second, right, into its vertical and horizontal parts, like how I told you in the last video. Yeah, and I have me my angle theta, and the way that we split this up is just using simple trig. Yeah, sine, and let's call this vertical part as let's call this give this a name. Okay, let's call this y dot 0. Reason why is this is a vertical velocity, and 0 is like at time 0, or initial, like, you know. This notation also works in physics to some degree. Anyway, this would be x dot 0 in that same, following the same logic. Again, these can be given any arbitrary name, u, b, as long as it doesn't have a specific meaning. It can be a smiley face, a love heart, or something. Really doesn't matter. Yeah. Okay. So sine of theta is equal to y dot y naught dot over 12. So that means y dot naught, my initial vertical velocity, is equal to 12 sine theta. Following the same way for cos, then I get x dot at 0, like origin bingo, is equal to 12 cos theta. Theta, not 0. Yeah. Okay, now what? What can I do with this? This is pretty useful because now I have my x is equal to, now I have my coefficient of time. Remember, like that coefficient is this initial vertical velocity. So I have actually x dot naught time times t plus, let's call this first constant. Yeah. This is my initial horizontal velocity. So I can substitute that back in as well. So that means I have 12 t cos theta. Remember, theta is a constant. It's not changing here. C1, yeah? And I have my y, which is equal to minus g on 2 t squared, plus now my initial vertical velocity. So that is 12 t sine theta. The t is being multiplied here as well, because remember there's a t outside in the general equation. I just put that in here because I don't want to get that confused within the sign. Yeah. Plus now I'll write this as C2. Okay, C1 represents my initial horizontal displacement. Now it's most convenient for me to have this as my origin, my x and y and my y axis. Yeah, so just x and y. Having this at the origin makes its initial horizontal displacement 0 and its initial vertical displacement 0 as well. So in this case, both C1 and C2 are 0. And this is just the way that I put my axes, so that it's most convenient for me. Okay, now what about this? Let's do the same thing that we did before. Get rid of the t. The reason why we're getting rid of the t is so that we have the actual trajectory, the path that this football takes. Why I want to use this is because I'm given a point on that path. So then I would have t is equal to x on 12 cos theta. Remember, this is just some number, yeah? And I'm trying to figure out what that theta is so I can figure out that number as well. But anyway, substituting this back in, so I'd have y is equal to minus g on 2, x on 12 cos theta squared plus 12 sine theta times x on 12 cos theta. And that's it. Yeah? What can I do here? I can, actually what I'll do is I'll leave it at this. find the angle of projection. So now I am solving for theta, but I need another piece of information. Oh wait, I do have another piece of information. I have this point. When x is equal to 9, y is equal to 4. That's what this tells me. So that means y is equal to 4. So 4 is equal to minus g on 2. Now when x is equal to 9, so that's 9 on 12 cos theta squared plus 12 sine theta. 9 on 12 cos theta. That, yeah? Now what can I do with this? I can simplify this a little bit. 9 cancels out with 12. This just gets me a 3 and a 4 here. This 12 can go with this 12. That goes away, bye-bye. And so then I get myself a minus g on 2. Now there's a little bit of trig that we apply here. That 3 squared gets to 9. This 4 goes to 16, so 9 of it is 16. Now I'll have a cos squared theta, right? But that's on the denominator. So now if I want to bring that up to the numerator, I have to turn that into a sec squared theta. Okay. That's interesting. But I also have myself, now the 9 comes out, so I have 9 sine theta over cos theta. So that becomes a tan. Tan theta. Okay. What can I do with this? I need to solve for theta. What I can do is I can turn this into a quadratic. I can have minus, now I have a 9g on, what's that, 32, weird numbers. And instead of sec squared theta, let's put ourselves a 1 plus tan squared. Now this becomes a quadratic in terms of tan. 9 tan theta. Okay, now for this quadratic formula or the quadratic to work in total, this needs to be a 0. So then we'll have 0 is equal to, now subtract 4 on both sides. That's what I'm doing. So then I want to write this in a full quadratic form. So I have minus 9g over 32 tan squared theta. Now I have a plus 9 tan theta. I still have to remember this guy. That's a minus 9g on 32 minus 4. Okay, there's a lot of negatives here. It's easier to work with if I divide everything by -1, and if I expand this out a little bit. These questions with g is equal to 10, sometimes it's easier to do the math just substituting g as 10. So I'm going to do those things, those two at once, right? The 0 is equal to, now this becomes a positive, this becomes a negative, this becomes a positive, and this is also positive. Yeah, that's what I do divided by a -1. Okay, so this becomes 90 on 32. 90 on 32, that is 45 on 16. Simplifying the fraction. Tan squared theta minus 9 tan theta. These are just simplifying the fractions. I'm not dividing by anything. Plus, now this is the same fraction as that one, so that's just, I get, again, 45 on 16 plus 4. Okay. Now let's we are using our quadratic formula. The tan theta, that's, yeah, the thing, is equal to that negative of that's 9, plus or minus square root of minus 9 squared, which is 81, minus 4a, what's a? A is this guy, so that's just 45 on 16. C is this thingamajig. Okay, it's easier to put this in a one fraction, so I'll just write this as 45 on 16 plus 4 is just 45 plus 64 on 16. Sorry, this is a side note. I just don't have my calculator on me, so I'm just winging this. So that let's just 64. That's what, 109 on 16. So I'm just substituting that in as well. 109 on 16. Okay, and this is all over 2a, so 2 times that, so that's just 45 on 8. Oh well, this is one heck of a quadratic. Okay, so then we have 9 plus or minus square root 81 minus the 4 can go with that thing, and that becomes a 4. So then we have a 45 times 109 all over 64. That's one really messy quadratic. Yeah, you really need a calculator. Number 1 lesson in math, don't forget your calculator. Because without it, you can't really solve very much, can you? I'll look up at this. Does this calculator work? Nope. Alright, let's do this. 45 on 4. 45 on 4 times, what am I timesing by? 109 divided by, what am I dividing by? 16. That thingo. So I'm gonna approximate 76.64. 1. I approximated right, okay. Over 45 on 8. Okay, 81 minus this thingo, right? 81 minus that thingo, 76 point, that thing, yeah. 76.64, 0625. It's 4.3, I'm going to round it to 4.36. I know my rounding isn't correct technically, plus or minus 4.36. Right, okay. This is over 45 over 8. So 45 over 8. Okay, square root of 4.36. I can take the square root of this. That works good enough. 2.088. Yeah. So now that's just 9 plus or minus. Not square root. I have plus or minus 2.088. I approximated right? Yeah, okay. I did. All over 45 over 8. Why did I leave this as this? I'll just substitute that in as well. 45 on 8. 5.625. I really need to put these on the calculator, but I don't have a calculator with me. Sad life. 8 on, what's this all on? 5.625. Okay. Now, let's put this in. So then I have 11.088 all over 5.625. That's a little bit over 2. My other answer that I get, 9 minus that. So 9 minus 2.088, I think. Yeah. 6.912. 6.912 all over 5.625. Okay. That's fine, that's fine. Okay, now this is what tan theta is equal to, my two numbers, yeah? These two. Okay, so then what's theta itself? So that means if tan theta is equal to this, right? Then theta is equal to the tan inverse of this. Yeah, so tan inverse of that thing, 11.088 over 5.625, or tan inverse of 6.912 over 5.625. Okay, I don't know if I can I'll do the division first. 11.088. Sorry if I'm taking so much time. 5.625. Alright, that thingo. Right, it's not over 2. Guess it's under. Okay. And if I have to take the tan inverse of this, it's around 63 degrees. So this is like roughly 63 degrees. Okay, and the other one, 6.912. 6.912 over 5.625. I get myself a 1.2288. Okay, just making sure if I'm right. Okay, and this is that's enough to take the tan inverse of that. It's around 51 degrees. Rounding correctly. And these are my two answers that I get. And those should be done. Those are your two angles that you get. And those are your angles of projection through which the football is kicked. I probably made a mistake somewhere here. If you can find it, thanks. Let me know. Alright, have a good time.